problem, and this one is going to be a repeated quadratic factors problem. We've been given the integral of x cubed plus x plus 1 divided by, that's already taken care of. We have x to the fourth in the denominator, so 4 is our largest degree. We have x to the third in the numerator, 3 is our largest degree there, so the degree of the denominator is greater than the degree of the numerator. So that part's taken care of. If that weren't the case, if they were equal or the degree of the numerator was greater, we would need to use polynomial long division to fix that. But in this case, that's already done. So now our next step is to factor the denominator as completely as we can. So what we're going to have is x cubed plus x plus 1, and then in the denominator, we're going to have x squared plus 1 times. To that, we'll get the entire denominator from the left to cancel out with this value here, leaving us with just the numerator x cubed plus x plus 1. Over on the right-hand side, when we multiply this quotient here by this x squared plus 1 quantity squared, we're going to get this single factor to cancel from the denominator and one of the factors to cancel from the numerator. So we're going to be left with this ax plus b multiplied by just one of these factors, so x squared plus 1 to the first. Here, though, with this quotient, we have x squared plus 1 quantity squared in the denominator and x squared plus 1 quantity squared in the numerator, so both of those are going to cancel, leaving us with just cx plus d. Now we need to simplify the right-hand side by distributing this ax plus b across the x squared plus 1, so we're going to FOIL this out. So ax times x squared is ax cubed, ax times 1 is ax, b times x squared is bx squared, and b times 1 is b, plus cx plus d. Now what we want to do is collect like terms. So the only x cubed term is this ax cubed, so that'll be left by itself. The only x squared term is bx squared, so we'll leave that by itself. But then now we have constants here, a, b, c, and d. We want to solve for each one. Well, we already know a is equal to 1 and b is equal to 0, so we just need to solve for c and d. If a is equal to 1, then this equation right here, instead of a plus c, becomes 1 plus c equals 1. Subtracting 1 from both sides, we can say that c is equal to 0. Here, since we know that b is equal to 0, we can plug 0 in for b into this equation, and so then it's
imaginary picture. Usually it's something that moves.
Instead of b plus d, we're going to get 0 plus d is equal to 1. Of course, that's just d equals 1, so now we have all four values for the constants. What we want to do then is plug that back into our partial fractions decomposition. This value right here, the sum of